Within this video in Chapter 6, we're going to consider concepts involving quantum mechanics and atomic orbitals, how we represent them with quantum numbers, and begin to think about them as contour models. So in this section, the book lists two different objectives. We want to be able to compare and contrast atomic orbitals used in Schrodinger's model of the atom with the orbits used in Bohr's model, and analyze allowed quantum numbers for a given atomic orbital. Here's a description that we had of Bohr's model of the hydrogen atom. So their electron is being defined as being in a particular orbit, these concentric circles. We have different energy levels corresponding to the different orbits in the corresponding emission spectrum. So within Bohr's model, the position of the electron is well defined. We have a ground state, n equals 1, in different excited states, and this transition from a higher to a lower energy level emits a photon, and that's what's being recorded here on the emission spectrometer. So what's the Schrodinger model like? So within the Schrodinger model, it's including both a wave-like and a particle-like description for the electron. The equation is given there at the top. We're not going to be having any reason to analyze that, but we will look at the results. So we will qualitatively consider Schrodinger's model. And we're going to be looking at that for the simplest of atoms, hydrogen. So here's a depiction in the same sim of the Schrodinger model. I see some similarities, but also differences. The position of the electron here, I no longer see these concentric orbits. Seems like it has a strange, eerie representation. We have different energy levels. They're similar, but I see that they're broadened out a little bit. It's not just n equals 1, n equals 2, n equals 3. There's different features as well. These are precisely known. When we have the transition from an electron from a higher to a lower energy state, a photon's emitted. And when I say it works, I mean it gives a really good prediction for the emission spectrum for hydrogen. To reconcile this with the Heisenberg uncertainty principle, we're going to precisely know the energy levels, and that will mean that the position is now ill-defined. We won't have as much information as we did in the Bohr model of where the electron would be found. So the representation here, instead of, again, having concentric circles that we called orbits, we're now going to call them atomic orbitals. They describe the probability of finding the electron in a particular region of space. That's what they're trying to show with the different colors. These orbitals are going to have quantum numbers that describe their shape and the energy. Instead of having one quantum number like in the Bohr model, we're going to have 4. N, L, M sub L, and M sub S. Here's a fuller description of the Schrodinger equation. And here are the different quantum numbers. So several of these, N, L, M sub L, they're features within this broader equation. That's where they're coming from. M sub S, that's one that we add in later. It wasn't part of Schrodinger's initial description. So what are we going to do with that? We need to understand what each quantum number is telling us and how their allowed values lead to particular atomic orbitals that electrons may occupy. So by allowed values, I'm talking about this region right here. There's different relationships between the quantum numbers N, L, and M sub L. So we need to understand those, and also then what they correspond to. In the Bohr model, we only had a single quantum number, the principal quantum number n. Now, the atomic orbitals here are more complex, so we need more information to describe their size, shape, and orientation. So let's explore then the energy levels in the hydrogen atom. So we're going to begin with this picture right here. What I'd like you to do, pause the video, grab a piece of paper, reproduce this initial sketch. We're going to add more features to it. So grab a piece of paper, write it on a similar scale here, and add n equals 1, n equals 2, n equals 3. Reproduce the image. So the initial quantum number here is the principal quantum number n. This is the same as in the Bohr model. Notice within the energy, this could be considered the potential energy. Recall that our reference potential energy is when the particles are attract to each other but have a large separation. The attraction here is between the proton and the electron. For hydrogen, it seems like in addition to indicating the size, it's also indicating the energy. Let's add these features next. Each box here corresponds to an atomic orbital. Add this to your sketch. I'm also adding then the corresponding L values. This column here is L equals 1, L equals 0, L equals 1, L equals 2. That's what it means to have allowed values here, beginning at 0 and going all the way to n minus 1. The L values have different letters that you may have heard before describing different types of orbitals. When L equals 0, that's called an S orbital. 1 is a P, 2 is a D, 3 is an F. So this whole column right here would be a principal quantum number and then an S orbital. 1s, 2s, 3s. Next to that is an L equals 1 column. That would correspond to 2p, 3p. Based on the system, what's going to be the designation that goes here? Add that to your drawing as well. That would correspond then to a 3D. Where does the magnetic quantum number m sub L fit in? The allowed values go from L, L minus 1, all the way from L, spanning from L all the way to L minus 1. Let me show you what that means. So within this column, the L value here was 0, m sub L therefore is 0. L equals 1, it goes from L all the way to minus L in whole numbers, so it's 1, 0, minus 1. For a L equals 2, I see 2, 1, 0, minus 1, minus 2. That's the relationship then for the allowed m sub L values. Notice how it's related to the L. So, like, you pause for a second now. Are you able to continue this pattern if we have n equals 4, n equals 5? What would the rest of your diagram look like? So here I was trying to make sense and begin to compare and contrast the Schrodinger's model with the orbits used in the Bohr model. This idea of saying whether we have particular quantum numbers allowed. The book has this particular table that lists different values and also includes this figure. What I've tried to do is take that figure and add in the other information, like where the m sub L values are coming from. This particular image, whether you can sketch it or refer to it, I think it's a really useful one if we want to consider whether particular quantum numbers are allowed or not. If you want more information on this part, as an additional resource, check out the interactive sample exercise in the book. There's a video that describes the same feature. Let's then look at a few different problems. So take a second, pause the video, see if you're able to answer these. The kinds of features I'd like to bring to your attention. So first of all, this question is referring to the hydrogen atom. And the principal quantum number n, that determines the energy of the atomic orbital. We'll see that that is not precisely the case when we're looking at other atoms, but it is for hydrogen. And the angular momentum quantum number, that's what's determining the shape. To answer this one right here, it says an orbital has n equals 4, m sub L equals minus 1. What would be the possible values of L for this orbital? So I've sketched out here what I think we have taking place when n equals 4. 4s, 4p, 4d, and 4f. If I highlight the ones that could possibly have m sub L equals minus 1, I see that for a p orbital, a d orbital, and an f orbital. P orbital, d orbital, and f orbitals, those have L values of 1, 2, and 3. Let's consider this question. Which of the following statements about the 3D subshell of a hydrogen atom is false? Let's recall each box in this orbital diagram is where the electrons are placed. This is called an orbital diagram when you have the different boxes that would be shown to hold electrons. You could have 0 electrons, it could have 1, or it could have a maximum of 2. the electrons that we placed in there are going to have different m sub s values. That's our last quantum number. M sub s referring to what's called the spin. Each of these boxes then can hold up to 2 electrons. With that information, see if you can answer this question. Here's another end of chapter 1. It says, for the table that follows, write which orbital goes with the quantum numbers. Don't worry about x, y, z subscripts. If the quantum numbers are not allowed, write not allowed. I think several of these we have a good understanding and would be able to address. Give this one a try. So if I'm initially just looking at the n value and l value, I would have a 1s orbital, a 3d orbital, a 4d, and a 5f. Can you explain why these other ones are not allowed? What's incorrect when you're looking at these other combinations that I think are not allowed? Now this idea here of don't worry about the subscripts, this is getting at another feature. The magnetic quantum number m sub l, that was describing the orientation in space. That's what's being given here with different m sub l values. So when I say different orientations in space, we have to understand then what the different orbitals look like. So first thought is that these atomic orbitals, they're telling us the probable location of an electron. The shape of the orbital for an s is a sphere. There is no preferred orientation. For an s orbital, if it looks like a ball, you can tumble it any which way and it still looks the same. That's what it means to say there is no orientation to it. M sub l equals 0. This idea that it tells us the probable location of an electron, look at this first representation here. This is showing a lot of different dots. Where you see more dots, that's the more probable location of finding the electron. More dots are found towards the center, less and less frequent as we move further out. Now, instead of drawing all those dots all the time, you see these kind of representations. If you look at the description, it says each sphere encloses the volume in which 90% probability of finding the electron. So we have an s orbital, 1s, 2s is larger, 3s is even larger. In each case, instead of drawing all the dots, they're saying this sphere would enclose 90% probability of finding the electron. Here would be representations for the p orbitals. Once again, the atomic orbitals telling us the probable location of an electron. The shape of a p orbital, I see 2 different lobes. There are 3 orientations in space now. The m sub l values are telling me the number of orientations. With the m sub l values, I see allowed values of 0, 1, minus 1, 3 different orientations, 3 different boxes I'd be filling in. That's what those subscripts now are designating. PZ, PX, PY, they're showing which axes those 2 lobes are centered along. Along the Z, along the X, along the Y. We should be able to predict then how many orientations would we have for a d orbital. The shape of the d orbital is more complex, but it's very recognizable. For all of these, I think you should be able to recognize is it an s orbital, a p orbital, or a d orbital. And there are 5 orientations because they have 5 different m sub l values. For the most part, those are showing which plane the sets of lobes are along. Just as an example here, dxy, these 2 sets of orbitals are in the xy plane. Here's another self-assessment question from the chapter. As the value of the principal quantum number n for an orbital increases, which of the following statements is true for an electron that occupies that orbital? Take a second, read through the choices. I think this one, in order to answer it, is coming back to what these different representations are describing. Give that one a try. So to wrap things up, even though we haven't looked at the completing the mathematical calculation involved in the Schrodinger equation, I think we've made some progress of being able to understand different representations. So we've made sense of these ghostly images because they're no longer literally saying where the electron is found. It's describing a particular region of space where we have a probability of finding the electron. And the particular shape then is described with these different quantum numbers. That's why we have this designation N, L, and M sub L. These would be the different quantum numbers. One additional feature though within this, it looks like there's these regions in between that are dark where the electron would not be found. I think we need to learn more about that feature of the atomic orbitals. So within this video, we've looked at introducing the idea of quantum mechanics as it pertains to atomic orbitals. We've spent time looking at quantum numbers that describe the shape and energy of these orbitals. And as far as representations, we looked at contour models. We're going to extend that next time in class by looking at what are called radial probability distribution functions.